everybody. Thank you very much for joining us here today. You are in the right place if you are here for our webinar on what you need to know when routing DDR3 Part 2. Our presenter today is going to be Sean Kelly, followed by another colleague of ours, Tom Cassidy, who's going to show a practical aspect of DDR3. Before we turn it over to Sean to begin, just want to let you know that we will have some time for questions. So please do take a look at your questions panel over there and write those questions as you're going along. And we'll take some time to answer those. If we can answer those during the webinar, we'll certainly do so. If not, we'll certainly contact you thereafter, or we'll publish a Q&A sheet. So with that, since we have a lot to cover, I'm going to turn it over here to Sean.
Well, thank you everybody for joining me today on Part 2. Hopefully you got a chance to see Part 1. So let's go ahead and get started. And in Part 1, to do a real quick review, the DDR3 signals, we talked about them being grouped into two specific sections, the address, command, and clock, and then the data section. We also talked about a new concept that was applied to the ACC group, and that is fly-by routing concept. We also talked about the match length versus match delay. We spent quite a bit of time helping everyone to understand the difference between matching length and then dealing with the time associated with propagation. And so therefore we made sure that your signals actually arrive simultaneously based upon the delay and not necessarily the length. In Part 2 today, we're going to talk about some high-speed techniques that pertain specifically to DDR3. We're also going to talk about serpentines, accordions, and some people refer to them as meander lines. I'm also going to talk about On-Die-Termination. That's a term that you'll hear quite a bit associated with DDR3 and can be kind of confusing. Then I'm going to wrap up my section with thoughts on vias. I'm not going to go into a whole lot of detail, but just kind of give you an overview. And then Tom's going to take over and talk about xSignals, pin delay, and pin swapping. Before we get started, I'd like to ask you this question about why are you attending this webinar specifically? If you would, please answer this. Okay, thank you very much. So basically, most of you all just want a better understanding of DDR3 in general. Okay, so when it comes to high-speed routing techniques, I have covered this in depth in previous webinar series called Enough with Theory Already, Give Me Some Application. And if you want to watch these, please contact 9.connects and we'll be more than happy to get you a link to that webinar. The goals when using these type of techniques is basically broken down into two sections right now for this webinar. The first section is going to be dealing with minimizing signal attenuation, maximizing your bandwidth, and then minimize your reflections. The minimize crosstalk and minimize radiation. The radiation aspect is more for making sure you don't fail FCC tests. But all of these high-speed routing techniques that we're going to talk about in some way or another deal with these goals. Now this is a very common waveform of an eye diagram that most of you all are probably already familiar with. But if you're not familiar with it, let me just go over some real basics. So you have this red square here that defines what we call an eye opening. And so we have to have a high, logic high, be higher than the top of the square. And then we have to have a logic low being lower than the bottom of the red square. And then obviously on the transitions, we want these transitions to be sharp enough so the left hand and the right hand edge of this eye stay open as well. Now, we want to talk about attenuation. The attenuation of the signal is going to affect the top part of this waveform, and it's going to be a function of the PCB loss tangent. So you need to be aware of that factor of the material that you're dealing with. The rule of thumb is that the lower the loss tangent, the better off you are, therefore the less attenuation. Be aware that your total loss is going to be a function of length. Obviously, shorter runs are going to be better then. If you'll notice here on the right, bottom right, you can see a really good eye diagram on the left here, And then on the right, you can see when there's significant attenuation on the waveform. You also want to make sure that you don't have limited bandwidth situation, because if you do, you have greater losses of those higher frequencies. Those higher frequencies are what give you this nice sharp slew rate here. So you can see when you limit the bandwidth, the slope becomes much slower and you're starting to close in on the left-hand and right-hand side of the eye. That loss of higher frequencies is what contributes to the slower slew rate. When you're minimizing reflections, you need to be aware of transmission line mismatches. So again, you can see on the right-hand side an effect shown by a mismatch. And you can also get quite a significant change in waveform if you have a transmission line discontinuity. Some general routing rules. Talk about pad exits. A lot of these memory controllers are FPGA packages. So trying to deal with a fan out, you need to be aware of these type of goals. Especially with the differential signals, you want to reestablish that differential impedance as soon as possible. So that basically makes your goal to make sure the spacing is appropriate. With lumped components, your goal, again, is you want to maintain the differential impedance as much as possible. Anytime you spread fields between the two traces, you're increasing your probability of either crosstalk or radiation. And also in this situation, you would be increasing impedance mismatch. Yes, the section here in the middle is the preferred way. Now, some people might say, but it may not be necessarily that big of a deal. Here's my thought on this whole concept as we go forward and you're looking at the slides. You know, you can try and make sure you cover all your bases. So just in case you miss something, you have kind of built in enough slop to make sure that you've made a little extra room for that slop. If you treat like all these general routing rules as, it's probably not a big deal because that's a lump length, not a transmission line, then they can all add up quite significantly. Now with anti-pads, most of you all are very familiar. When you put a via in a board, there's a clearance around that via to any surrounding areas, especially the copper pores that end up being your reference planes. So you want to make sure that if you have a via nearby, that you want to make sure there is no clearance of the reference plane underneath one of the traces. Pad entrance and exit. The right side has an abrupt impedance change. Yes, again, you'll hear some people say, well, as long as that length there in this section right here is a lumped element, then you can disregard it. Again, all I'm saying is that the left-hand side is a better representation of what you could do, and it doesn't cost you anything. Again, when it comes to reference planes, if you have a plane void, especially if you've done any kind of RF circuits where you may have, let's say, a Bluetooth antenna or something like that, some kind of RF module, they'll have a huge clearing in the plane beneath it. So you want to make sure that that plane void is not underneath or anywhere near your differential lines. And also you want to maintain reference. We're going to talk about this a little bit more later on in the presentation, but you want to add your vias to tie the reference planes together to keep your common mode impedances balanced. Anytime you have a mismatch in that common mode impedance, you can create common mode noise and cause increased radiation. So polling question number 2, I'm curious, because we're going to talk about serpentines next. How often have you ever done serpentines, and how comfortable do you feel creating serpentines? Okay, thank you for that. Okay, so actually there's quite a few of you all out there that have never created anything before. Okay, good. But a significant portion of you actually feel very comfortable. Okay, good to know. So these serpentines, meander lines, or accordions, they're used extensively in DDR for the purposes of matching length and delay. Now, last month when we had part one, I gave an example of routing a signal on the outside of the board, otherwise known as a microstrip, and then comparing it to running that same signal interior to the board, known as a strip line. And so I just want to clarify that in this situation where you might happen to route data lines from a same group, such that one of the data bits is on the top and one of the data bits is in the bottom, you definitely would need to compensate for the slower strip line layer. And so you would need to put a serpentine in the microstrip in order to make sure you dealt with the faster speed of the microstrip. You can also use these serpentine type devices to create matches within layers. If you're familiar with Altium, you'll notice this is an interior color that's used quite often. So if this is a data group, you can match within the data group to make sure that all the skews are the same. In DDR specifically, most strip lines are used for strip lines. One of the recommendations I made last webinar is I said you would be much better served by trying to take all of your signals and immediately put them into the interior of the circuit board and stay routing within the circuit board itself. Try not to do any of it on microstrip for a variety of reasons. But anyhow, you'll find that when Tom's examples, he's going to show you they'll be in the interior of the board. So what exactly is a serpentine? As we talked about last week, the basic concept that it takes time for a wave to propagate through a board material. And so we have to deal with that. We also realize that the specific length is going to create a specific delay. So what is the issue if it's not done correctly? If it's not done correctly, you can create crosstalk. Crosstalk can be detrimental to the signal being on the victim line that you're trying to use. You can induce noise in that, so the victim is not going to act properly. The other thing is the signal that you're trying to actually route through the serpentine may not be delayed as much as you might think. What you're going to find out, as we talk about later, is that your wave actually propagates faster in the serpentine than you might think. So you got to be aware of that aspect when you're creating a serpentine. If you create a serpentine to, let's say, do 150 picosecond delay based upon the length, you got to be aware that's actually not going to be that much of a delay. So you actually have to make it a little bit longer than you might have thought of. And then obviously, if you didn't calculate correctly, then the serpentine might actually be longer than necessary, and therefore you've increased the attenuation of your wave. When you're talking about serpentines, we need to talk about single-ended versus differential, and then microstrip versus strip line, because their behavior is different in each. So before we get into the actual design, let's talk a little bit about single-ended crosstalk, and what do we mean by that? Crosstalk is a means of transferring energy during the rise and fall of a signal. Common depiction of crosstalk via mutual inductance is shown below. The problem is it's kind of hard to understand this as it relates to a distributed inductance, because here you have a distributed inductance along the trace and then a distributed capacitance along the trace. So what I want to do is show you maybe another way of thinking about relating this crosstalk issue in parallel transmission lines. Now, I'm sure most of you all have already seen wave or pictures of what microstrip looks like with the radiating E fields. Well, those radiating E fields are going to also create forward crosstalk, because ultimately what those do is they create capacitance. So What is the definition of a capacitor? Two plates separated by a dielectric. So if I have a positive charge on my aggressor trace, I'm going to create a negative charge on the victim trace via those electric fields. But we also have inductive coupling done via the delta of flux density. So let me look at this diagram over here on the right, and using common notation where the plus sign is looking at the back of the arrow going into the presentation, so the current's flowing away from us, you're going to create a magnetic lines of flux in this clockwise direction around your aggressor trace. Well, if you'll notice, the density changes as you get away from your aggressor. So the net effect is you have less flux density on the right side of the victim trace and a higher flux density on the left side. And that creates, as far as any charge within this victim trace, a counterclockwise B field. Well, a counterclockwise B field is the same as the current coming out of the board toward you. So in single-ended crosstalk, a lot of you all will probably be dealing with systems operating under 1 gigahertz or rise times greater than 130 picoseconds. And these are realistic separations, with H being the thickness of your substrate, then separation between microstrip being 2 times that thickness is sufficient typically. And then in strip line, only 1 thickness of the substrate. But as your frequency content gets higher, you have to approach the ideal, even if the ideal is not necessarily practical. Because as you increase that separation, the electric field is going to dissipate as well as that magnetic field, and so therefore there'll be less and less coupling. So if you do a study on it, you'll find that in this amount of separation, there's virtually no noise contributed to the victim trace. Now for single-ended microstrip serpentines, you're going to use these typically on your address, data, and your control lines. What I've shown you here on the right is a picture of one portion of a meander line or serpentine, where the signal comes in on the left-hand side, goes and turns and comes back. And then of course it keeps on going. I just want to show you this one because we're going to talk about this gap that exists between this coupled length. You have to treat this as a mutual coupling, both capacitively and inductively. If the gap is 4 times the substrate thickness, the speed in which the wave is traveling is slower. Obviously, you're going to get less crosstalk and therefore less noise. And in fact, the delay in a serpentine that has a nice size gap is pretty closely matched to a straight route. As you decrease the gap, you end up taking less real estate on your board, but the problem is you create more crosstalk and the wave becomes faster. Remember that separation gap is one goal, but another is to minimize the length of the coupled serpentine sections as much as possible. This will also reduce the total magnitude of the coupling. So let's go in a specific example. If I take a 12-inch line, straight line, that's represented by this red waveform, and I'm going to compare it to a gap with 5H basically. So on your waveforms over here, green is your source signal, red is going to be the 12-inch straight line, as I said before, and the blue, which you don't really hardly see at all, is the waveform at the end of this 5-gap example. The only thing you see is a little bit of crosstalk created right here. The thing you want to notice here, though, as far as timing is concerned, is both the reference and the serpentine have virtually the same delay. So in other words, the serpentine itself is not faster than just a straight piece of wire or transmission line. There is a little bit of difference. It's 15 picoseconds. So if you're dealing with a clock, just be aware 15 picoseconds is about 7 times more than the skew you want. So as we increase this coupling, I want to show you that you can see that in the blue trace, here's the output of a closely coupled example. You can see a significantly more reverse crosstalk and a little bit more forward crosstalk. The reference and the serpentine obviously have different delays now. This delay ends up being 150 picoseconds. So why the difference? Well, contrary to what you may believe, the propagation delay of a serpentine trace might be less than the delay through an equivalent length of straight trace if the gap is not sufficient. And the signal sped up because a portion of that signal is going to propagate perpendicular to the serpentine. So in a nutshell, what I'm trying to say is you need to increase your gap and utilize more real estate is something you want to strive for as much as possible. It also gives you much more accurate skew compensation. If you're in a situation where you can't do that and real estate is a premium, then just be aware of the delay so you can compensate for it. So here's one of my favorite examples that I'd like to use again. And it has to deal with differential traces going between a driver and a receiver, and you have pair A, pair B, and pair C. And so the goal is you want to keep corners at an equal count. It seems simple, but it's actually a common error when people routing it. So this next question is, I'd like to know, if you're looking at this diagram, which pair do you think is the problem? So very good. So 32% of the people out there are either very sharp or have seen my webinars before. So yes, the answer is D. A and C is the correct answer. So the concept is balancing the inside and the outside ratio. In pair B, you have a short, long, long, short, short, long on one side of the differential pair, and long, short, short, long, long, short on the other side. So both lines have the same amount of outside and inside corners. A and B, or A and C, do not. So, and specifically pair A, you'll notice that the signal here on the bottom red line would definitely get to the receiver sooner. Now with differential serpentines, which are in DDR3, we're referring to the clock and strobe, you want to remember that your goal is don't overstretch fields. You'll hear me say this over and over again. You don't want to stretch fields any more than you absolutely have to. So I've given you an example here of some general rules. Is based upon the spacing between the lines. You don't want this part of the serpentine to be further away than twice that of the actual spacing of the main pair. And then again, you don't want these transitional portions here and here to be too close because they will create coupling. So the question is, why would you need this on a clock or strobe? It's because you want to possibly match the clock and strobe to another signal. Now, specifically in the flyby routing, when you have a clock that's leaving the controller and it's going to go from one chip to next chip in this daisy chain fashion, you just need to make sure that it arrives at a certain time relating to other signals within the whole system. But you also could possibly have to deal with minimizing a skew within a pair itself. So an example that you see over here in the green line is as the differential signal leaves the FPGA, you want to make sure that you reestablish the timing involved. So if the wave comes out at the same time, then this waveform up here is going to be stretched. And so if you slow down this waveform, both the negative and a positive then become synchronized right here for the rest of the line. Two ways that you need to be aware of there you could have skew within a pair. If the turns are unbalanced, like we did in the previous question, or like I showed in the right, entry exit of source and loads. Now there's a common unknown cause of skew in differential traces, and that's the substrate itself. Many PCB layouts are done without any idea of how much the substrate can influence the differential skew. What you'll see below are 3 different glass weaves. 1080 is one of the more popular versions, and in this picture you'll notice specifically what a huge gap you have between the glass threads in the 1080 material. Well, what's going to be filling in that gap? It's the resin. In the other versions here, you see that the weave is tighter, but you still have to deal with the resin could be immediately underneath here, thicker than it would be underneath here, as far as it relates to the signal trace itself. But if we take an example on this 1080 material and I were to put a pair of differential lines on this material, and this is, relatively speaking, a real-time example of real widths, you can notice that one trace could be over predominantly glass, and then the other trace could be over predominantly resin. The thing that you need to understand is that the dielectric constant of the resin is significantly different than the glass dielectric constant. If we put one track on the glass and one on the resin, we can create a propagation speed as much as 0.5, a different dielectric constant as much as 0.5. That 0.5 difference in the dielectric constant can create as much as 10 picoseconds per inch in skew. Again, if you remember from last webinar, we talked about clock skews don't want to have any more than 2 picoseconds between the positive and negative terminals. So possible solutions. First of all, you always want to research the materials used by the board house as it relates to weave. You don't want to specify or use such loosely woven materials. And if possible, don't route your differential pairs along long straight lines. Now that rule itself has been around for a long time. Not everybody always understood exactly why. You also have the other option is to have the board house fabricate a PCB on 10 to 15 degree bias. You would basically stipulate that in a fab note, and board houses nowadays are very aware of this situation, and they're not going to balk at that. You can also rely on your input from the board house on material selection. Just tell them that you're doing some high-speed designs and you have a lot of differential signals and you need to be aware of this problem and what would they recommend. But understand that the PCB material itself is a science, and a good routing engineer is going to take the time to research the best material for the job. So polling question number 4, if you would, we're going to go into the on-Die-Termination concept before we get into it, is in previous DDR projects, how aware were you aware of the skew dilemma? Okay, interesting. So there's still 14% of you were not aware. Okay. 41% somewhat aware but not sure how to deal with it. Okay, good. Well, hopefully you'll find that this portion beneficial to you. So in last month we talked about in the ACC group we used 40 ohm termination resistors on DDR3 as one of the more common impedances. But this is referred to as off-die termination, and it works very well for flyby routing. And basically what you have is the memory controller here, and it's sending out, let's say, an address line, and that address line goes to your DIMM, and you have, or memory module, and then you have the 40 ohm termination here. But that's not going to work very well for what would be considered multi-rank situations. And so therefore, on-die termination had to be developed and optimized because of the way the data lines are going to be used. You remember the data lines are parallel from the controller to the memory module themselves. They're also shared by all the memory modules. So in utilization of the data, strobe, and mask group, there are basically two cases to consider. In a very simple solution where you just have a controller and one memory module, you have what's considered a point-to-point solution. Basically what you have is the driver sends out through a transmission line to the memory load. But you also have point-to-point or multi-rank designs, like I said, in what you would see in like your motherboard, where you have memory boards that plug in. In this first case, the impedance matching is much simpler. During a write, we would have the output impedance of the controller equals a transmission line, and that equals the input impedance of the memory itself. But in the multi-point case, we definitely need on-die termination. Obviously, each pin driving and loading the transmission line has its own impedance. The problem came when there were mismatches. On-die termination calibration is a technique that involves calibrating this termination impedance to deal with the mismatches. It also allows an optimal termination value to be established that can compensate for variations in process and operating conditions. Dynamic on-die termination provides systems with increased flexibility to optimize termination values for different loading conditions, i.e. what we're familiar with all dealing with motherboards, this multi-rank design. So for optimum signaling in a typical dual slot system, you're going to have an active and a standby module. The active module, you're going to want to set, not you, but the controller is going to ask the active module to set that impedance to higher than the normal 40 ohms. And at the same time, the standby module is going to terminate to a lower impedance, typically 30 or 40 ohms. When you do this, the standby module is going to absorb the signal that was sent to it and cause less of a reflection back to the active module. That means the active module more than likely will get a better waveform. So the benefits of on-die termination is it will reduce the amount of jitter at the active module in a point to multi-point system. It does this by decreasing the reflections from any secondary modules. The dynamic on-die termination also improves the bus scheduling with seamless transitions between nominal and write termination values. And the interesting thing about this is the calibrated value is going to significantly reduce unwanted signal reflections and yet create minimal attenuating of the magnitude of the signal swing due to this resistive loading. There's a great app note here that I would recommend if you're not that familiar with this concept. Please feel free to check this out. Now, we talked on-die termination. Well, that was how we dealt with the memory itself. But when you're talking about the controller, you have something called on-chip termination. It's basically the same thing, but in reverse. What we were talking about before was a write to the DRAM. Now we're talking about a read to the DRAM going back to the controller, and it's used for fine-tuning of the input impedance of the controller. Be aware that both of these concepts have variations that are vendor-specific. So my purpose for this discussion was just to kind of give you an introduction to the concept, so that as you're reading these data sheets, you already kind of have an understanding of what is their goal when they talk about the terminology. Okay, so my thoughts on vias. Because it is the best way to always think of a signal moving through a PCB connector as a wave, it is always best to approach vias as a differential transmission line, even if it's single-ended. But all too often, people that are not really familiar with high-speed design, they see vias as a strictly a single-ended structure. So let's look at the following. You have a USB connector on the top of a board. It's a typical through-hole board or through-hole connector. And you would have the positive and negative coming through the pins. And if you're routing it properly, you would minimize the excess stub length by routing on the bottom of the board. So let's just say you were doing a design review on a coworker's work, just making sure it was done right. If you found the positive signal coming directly to the bottom, but the negative signal went down to an inner layer first, routed along the inner layer, and then popped down to the bottom, what would you think? I guarantee you would say to that person, I think we need to do some more training on how to properly route USB signals. The problem is what you're doing by treating all vias as single-ended is basically the same thing. Most people don't treat the reference plane portion of the wave in a single-ended application as important as the negative in the differential situation. That is the wrong approach. It's going to get you in trouble. It might work in low frequency situations, but it's not going to work in high frequency situations. So if you have a via and you have this in a single-ended situation, your signal layers on top and it propagates through and immediately goes down to the bottom, well, you have a very easy transition from the reference plane. But if you have two layers that are separated by a certain dielectric thickness, let's say, there's multiple layers in here, well, then this plane is not connected to this plane. And so therefore, there's no way for the reference to get from plane to plane. Here's probably the best picture to help understand what I'm referring to. It is imperative that in your path that you want to have relative to the signal a reference plane, some refer to it as a return path, such that the characteristic impedance can be maintained along the whole transmission or path that your wave is going to move through. Again, and I say this over and over again, you don't want your electromagnetic fields to deviate. You want them to be consistent as they move through your path. Any deviation of those fields is because there's a deviation of the inductance in the path and or the capacitance around the path. So the goal when changing layers is utilizing vias in a return path that allow for the electromagnetic fields to maintain the shape as much as possible. So basically, as your signal is moving along this blue trace, let's say it's a microstrip, and it's relative to this reference plane here, you want to maintain this separation that creates this capacitance. And again, your transmission line has a characteristic impedance, which is relative to the ratio of the inductance to capacitance. You want that capacitance to stay the same even as the conductor moves through the stack. So you have to basically create the parasitic capacitances in that situation through that hole. And then consequently, you also want to make sure that you tie the reference planes together with this over here so that you have a path for the return, and therefore you've created inductance here. The goal is you want to mimic in the via situation the same capacitance and inductance that you have in your actual transmission line. Now, in this following session, like we said before, Tom is going to demonstrate some practical aspects such as pin swapping, how to incorporate pin delays, xSignals, which is unique to Altium, and then his example of a layout. So with that, I'll give this over to Tom.
Thank you, Sean. Can you hear me? Just want to make sure.
Hear you.
Now I just need to show my screen. See if that works. Okay, can everyone see my screen?
Yes, sir.
Okay, so what I'd like to do is just give a quick overview of a sample design I've done recently. It involves using an FPGA. This is a Xilinx FPGA. So these are the pins associated with the DDR section of that FPGA. I have two DDR3 chips that are connected. So this is chip number 1, chip number 2. These are the signals, and then above them I have the power sections. And then I have the termination for this. Since we're using flyby routing, we'll need termination like Sean mentioned. So I've got the termination resistors over here, and then I use a power supply dedicated for the termination voltage. As Sean mentioned, I'd like to show you a few things that typically aren't really thought of when you're doing this. One is the pin package delay. And Altium lets you do this, incorporate this into your design. Pin package delays are basically the delay that's involved between getting the signal off of the actual die in the chip and getting that to the pin. And if you're familiar with how chips are made, there's usually a very thin wire, or whisker wire, that connects the two. But in the larger packages nowadays, these different wires can be different lengths, and they can actually introduce a fairly significant change in your timing. And so what you need to do is take that into account before you do your delay routing on your circuit board, or you could have perfectly matched traces, but the internal delays within a package can totally throw everything off again. So in Altium, basically what they let you do is edit. You can assign a value to each pin. And Altium uses distance measurements. They don't use delays. So what you have to do is convert any delays you get from the manufacturer into an equivalent distance of trace, using the basic formulas for the dielectric constant. So as you can see here, I've got a lot of pin package delays, and just to give you an example, the shortest one is 351 mils of equivalent length, and the longest one is 694 mils. So you can see that's a pretty significant difference in effective trace length, which is why you really need to take that into account when you're doing your length matching. And then another aspect that we'll get into a little bit further, but you need to prepare for here, is the fact that a lot of controllers will give you, they're called hard controllers, and they basically define the pins for you and you can't change them. And this is not always really true. You can't change the signals, but within a byte lane, you're typically allowed to change the bits within a byte. So for example, for byte lane 0, you have bits 0 through 7. Just because they're assigned to these pins in the spec sheet doesn't mean those actually have to be the bits. And the reason they do this is to allow you some flexibility in routing. The chip manufacturers recognize that routing is difficult sometimes, usually. So they want to give you as much flexibility as possible. And then Altium also supports that by letting you define basically bit swap pins. So what we can do in Altium is basically set up a configure pin swapping. So what it lets you do is, if you see here, these are the byte lanes. So byte lane 0 through data bit 15. And I can define them in groups. So I basically define byte lane 0 as being part of 0 through 7, and then I define byte lane 1 as 8 through 15. And what this will do is later on, as I show you an example, this lets Altium let you swap lanes a lot easier than if you would have to manually go back and forth and swap them. And then one other issue is you want to make sure you define your differential pairs for your clocks and your strobe signals. Altium does this with these special symbols. So let me show you the initial PCB layout. Like I say, this is one FPGA, and there are two DDR chips. And so my initial thought here is, since I'm doing flyby routing for the address and control lines, the ACC group, I'm going to bring them out to the left side of the FPGA, bring them up, and then go across the DDR3 chips. And my intent is to put all my termination over here. So that gives me the initial basic outline of where things are going to go, and then the data lines are going to come straight up from the chip to the appropriate data bus pins. And then if you want to, at this stage, you can also define several net classes. Altium uses these to help you set up net class rules, routing rules. So at this stage, really all you need is just single and differential. So these are all the single layers, single signals, and these are the differential signals. So step 2, you can see I've actually started beginning the routing. I also defined additional net classes to help with the routing. So if I select the ACC group, you can see if they're highlighted, I followed my rules. So I basically come out of the DDR3 chip, come out to the left, and then we'll go across the two chips in a flyby configuration. This simplifies things several ways. The best way is that it gets everything away and gives me room to add in the serpentines as needed. So I'm not routing as quickly as I can. That'll end up tying me into a corner, and I won't be able to add any additional length that I needed to balance these out. And then you can also see For the FPGA, I did the initial byte lane breakout. So this is data byte lane 0. This is byte lane 1, and they both go to this chip. And then byte lane 2 and byte lane 3 are on the other chip. Another thing you might notice is byte lane 0 is on the orange layer, which is my signal layer 2, but byte lane 1 is all on the green layer. So I followed the suggested routing of alternating byte lanes between a chip. So if a chip has 2 lanes, you want to try to put them on separate layers. And then I've also got my clock signals coming off. I haven't routed them yet, but I did a breakout. And then also I've routed my termination from the second chip over to my termination resistors. And this is derived from our previous design, so I kind of already had the termination layout. One note here though is you want to make this as clean and solid of a plane as possible. So I basically got my power supply up here, and then I've got a nice path, well decoupled path for my resistors, and then the decoupling capacitors are spread around on the top and bottom layers. So you want to keep your termination as clean as you can with decoupling. So the third step is where I will basically finish off the ACC routing. So here you can see it's a little bit cleaner. It's kind of hard to see any difference from the previous one, but it's basically a finished routing. And then for the byte lanes, I'm taking advantage of the bit swapping capability. So basically what I did is the previous step, I had my byte lanes coming out as cleanly as I could from the FPGA. And then from the DDR3 chip, I do the same thing. I just route the pins as cleanly as I can, but without worrying about which pin is which. You still have to route the DM, the data mask line. So that's one chip, one signal you have to make sure you do because you cannot bit swap that. But the other 8 pins are bit swappable. And for Altium, I can show you real quick. They have a nice little effect of, I can basically say, okay, I want to make this signal connect to this signal. And what that little motion I just did basically connected those disparate net names on the schematic. So if I was to go back and show you those, they would now, the pins would have moved on the schematic, and these signals can now be routed together, whereas these are different, so Altium's not going to let me route them together. One other note you may have seen, I'm using 45-degree angle routing, and this is kind of a philosophical issue. A lot of people say, well, for lower speed, below gigahertz, you don't have to worry about the angle of the route. The issue being angles tend to have different widths on your conductor, and therefore you'll have impedance mismatches. So for Altium, routing in angles is very easy to do. They have the ability to add curves, to add arc lengths, but they're harder to work with. So if you do, even if you do intend to want to put in arc lengths, I'd recommend routing with angles first and then going back at the end and putting in your arcs. And then one other issue here is for the clocks. You see, when I routed them, you want to try to give as much room as you can because you may have to do some length tuning as well. So once again, try not to route yourself into a corner. Give as much space as possible. Another thing I didn't mention is when the data buses, I came out here, I have all this room over here to expand into. So basically when I do the length matching, I'm going to start by pushing stuff over, and I'll route these to the length match, move these as I need to, and as you'll see in the end, I'll end up filling in all the space. Let's see. At this stage is also when you might want to define what Altium calls xSignals. And xSignals are basically a way of combining nets, because on a net list, especially if you have termination signals or you have stubs going from one chip up to the pin coming back down, it's often very hard to calculate the actual electrical length based on just the net names. So Altium gives you the ability to combine them and come up with an actual electrical route as opposed to a physical copper route. And so over here you can see I've defined the address data group, ACC group, and you can see that it calculates the signal length for those signals. And maybe you can't tell, but they actually are different than the actual copper length. And another thing is in the xSignals, Altium also takes into account the pin package delay that we mentioned earlier. So instead of just the copper length, it's giving you the copper length plus the equivalent copper length within the chip. So at this point now, I'm basically ready to finish routing, and here it is finished. You can see, as I said, the data bus lines ended up getting expanded over. I took advantage of Altium's length matching tool to create some of these serpentines, and I'll show you that in a second. But then I also did what I call custom serpentines, where I needed to actually route manually up out of the chip and back down, just because there just wasn't enough room between here. And you may think, oh, this isn't quite following Sean's rule of 2x spacing and the serpentines and whatnot. But as Sean said, you've got to make trade-offs. And so even though this is a relatively loose design, sometimes you just got to accept the fact that the serpentines aren't going to be perfect. However, in defense of that, you can see that my routing is actually pretty amazingly tight. So I targeted a 3400 mil length for my address lines. And you can see using the routing tools, I was able to get them to within a mil or two, maybe up to 6 at the end here. So being able to get them really tight helps mitigate the fact that, yes, sometimes they may go faster than you'd like, but those changes are still going to be keep everything well within the window of your maximum and minimum skews. Just to show you a quick example of how Altium, they have an ability, basically you can select a tool and just say, okay, I want to route that, I want to route it to 3400 mils, and then it will automatically add in the serpentines needed to get to that length. And as I said, when I'm doing manual routing, I'll use 45 degrees, but for Altium, you're actually able to define the serpentines with arcs. So if you can, you might as well. It's a little bit better than normal, and it mitigates one potential problem down the road. And then just as a quick aside, Altium lets you export these values relatively easily to a spreadsheet. So I take advantage of that to create a custom spreadsheet that lets me to convert these lengths back into distances. And therefore I can double check that, based on the dielectric constant of the internal versus outer layers and the final lengths, I can just verify in the time domain that things are still pretty close, as opposed to verifying in the length domain. One other quick point, as Sean mentioned, you can see this is the top layer and this is my bottom layer. I was able to route all of the other signals on 4 internal strip line layers. So I am very confident that the timing I'm generating, the delays I'm generating with length is pretty consistent between signals. So I don't have to worry quite as much about different dielectric constants affecting my overall timing. So I think with that, I am pretty much done. It was a very quick overview, obviously not how to do it, but showing you the possibilities. And I'm going to go ahead and turn it back over to Paul, I believe is going to take over.
All right, thank you very much. Hey, Sean, I think you have one more polling question. Do you want to put that up?
Sure. Okay. So let me go ahead and just do a real quick summary. You can minimize probability of any problems by routing via strip line. As we talked about last month, you want to route your clock first, then your address and command signals, and then route your byte lanes individually. You can minimize coupling and serpentines is very helpful if you have the real estate available. Then there are compensation methods built into the controller and memory communication that can help with design errors, so you don't have to be perfect. When routing, always treat the signal as a wave moving through the PCB. Also included in this presentation is some reference material for you. So if you reach out to 9.Connects and get this presentation, you'll have this list. And the last polling question, if you don't mind, just help me to understand how we did today and how we met your needs. And when you finish with that, while Paul is talking to you, we'll look over the questions and get back with you. Thank you very much. And go ahead, Paul.
There we go. Well, thank you very much for attending this here today. Why are you here? Well, you're here for a reason, because DDR3 is definitely a buzzword that you've heard many, many times over. More so, you've probably gotten emails for software tools that say, hey, we can help you with this. And of course, there's a lot of articles that are constantly referencing it. So DDR3 is constantly something that everybody's talking about in terms of the way to go for memory. Of course, there's a lot of products that also contain it as well. So you are interested in it, but as you know, is it better to sit this one out, wait out for the next biggest thing, or is this the next biggest thing for the time to come? Are you sure about the source of the information? As Sean has mentioned, there's a lot of information out there. Not all of it's necessarily reliable. Hopefully, with these two webinars that you've been watching, you now have at least a baseline to go with over here. But we at 9.Connects really do want to provide a reliable source of information. Not sure the level of difficulty of it. You know, Tom showed you what it takes to do it. It's I'd say somewhat complex, but it's not impossible. And of course, there's always a worry about the risk when you're trying to take on something of this nature, because obviously this is more than a 4-layer board when you're trying to take on something of this nature here. So if you are looking to do things, you know, with DDR3, we can help you here at 9.Connects. We have plenty of design experience with it. We've done several designs as of late and been doing them really for the past year. So it's an area that we're very comfortable with. So we've completed several successful design layouts as of late, and we've done it with a number of different popular FPGAs, and we have done it with reference designs as well. So the question you may have is like, well, can't you just give me one of these things? And we'd love to. The problem is that it's really more of a service than for us to simply hand out a template. And it really comes down to this next point over here. It all depends on the board size, the number of layers, the manufacturing rules, the board material, the memory product that you're using, the transmission line structure. So there's a ton of factors that play into this before we could even start to lay something out like this. So if you are interested in this, we can either do it for you directly, or we can provide consulting services to assist you along with it so that you can be successful with it here. So for more information, check us out at 9.connects.com. And we've also put together a blog page, and I hope that we'll get some more information on DDR3 up on that blog page pretty soon, because we know that it's of key interest. So again, I want to thank you very much for your time, and we look forward to having you with us next month.